Welcome to my presentation on monitoring the water regime of the Rhine River from space. Objective of this study is the estimation of discharge from altimeter observation and intercomparison of discharge average. We choose a river with a dense network of in situ gauges to perform the validation of the result, the Rhine River. Three main groups of algorithms are used: the empirical, the semi-empirical, and the physical method. The input data are from altimeter and in situ data and the hydrodynamic model simulation. From space, the altimeter produces water level above the geoid and water slope. Satellite imaging produces river width and river mass. The model produces the same variables. In situ data are water level and discharge. We have 20 stations in situ of water level with height and partly discharge. The frequency of the data are 15 minutes. The hydrodynamic one-dimensional model, so black, is used. Shown here is the height above the local geoid. The model runs for different states: low, middle, high, and extreme is shown. The altimeter tracks of Sentinel-3A and B are seen here. We work with several altimeter datasets, the Copernicus baseline 3 and 4, and with the GPod Samosa Plus data. Here we present the water height retrievals of the OCOG retracker of the Copernicus product for an entire 400 km Rhine River reach between Maxau and Cologne. The number of virtual stations is 16. Based on the data availability and to the geographical characteristic, we have chosen a reach from Worms to Kaub. For our further processing of the discharge, we select the three reaches showed on the map. The Mainz reach is the reach after the inflow of the big Rhine tributary river Main. The Worms reach is the upper reach to the confluence. This area will allow an assessment of the method's sensitivity to the lateral inflow. The Kaub reach is quite a challenging area for altimetry due to the narrow river, the high banks, and the sharp slope. Different processing for level 1 data and in retracking, frequency output different have been compared. Different data selection to build the altimeter time series have been tested. Finally, the best dataset appear to be the GPod Samosa Plus dataset at 80 Hz, with standard deviation of difference of 10 cm in Mainz and 28 cm in Worms. There is a potential impact of sampling frequency on the discharge computation. The first methodology that we use to retrieve the discharge consists in the simple writing curve method. The altimetric water level and in situ discharge over the same time interval are used. A writing curve between altimetric height and in situ discharge are computed. This approach allows for correction of the retrieved discharge in the case of biased altimetric values. By developing a special writing curve for this height range, we can retain and reduce the uncertainties in the discharge retrieval. We will continue the investigation using the second and third proposed algorithm. Conclusion of this study are the following. The accuracy in terms of standard deviation difference of altimetry and water gauge depend on the altimeter product, data selection, and sampling frequency. The best accuracy is obtained with the GPod Samosa Plus with 10 cm standard deviation difference and 48 points in Mainz. The accuracy depends on the track configuration and is lower in Worms, parallel to the river. The river width variation is very low in the selected Rhine River reach. Therefore, the discharge is controlled by water level and water slope variation. Improved estimate of the parameter height will be produced in the ESA hydrocaster project. Thank you for your attention.